Okay, folks, we'll get started. So, this first survey that you've been working on, and please continue on it if you're still doing it, is on launch vehicles and staging. So, you've all seen the rocket equation. It's pretty simple, straightforward. Takes the ISP of the rocket, or the theoretical exhaust velocity of your rocket engine, plus the mass differential from start of your stage to the end of your stage, and it gives you an estimate of the delta V. Now, why do we stage? Is it for pure fun? Increase the delta V for a given payload? Increase reliability? We want to decrease reliability or decrease payload for a given delta V. I'm guessing most of you, well, some of you put decreased reliability. That's generally not something we aim for. It might be a result of something we do. And we generally don't like decreasing our payload for a given delta V. So we're going to do something that we want to improve. So we either want to improve our payload, or we want to improve our delta V, or both. The consequence, of course, is increased complexity. So those of you who put increased delta V for a given payload, that's the correct answer. So if we go back to our rocket equation, here, delta V is little ve natural log of m naught over m1. Now, anytime you do this, whether it be the rocket equation or the range equation for aircraft, always make sure that the larger number is on the top of your ratio. Because, of course, what happens if you take a logarithm of a number less than 1? It's negative, yeah. So generally, we're not trying to slow down in that sense. We're not trying to somehow magically take energy out of flight and put it back in the system. So our delta V is maximized when that ratio is the largest it can be. And what that means is all of that ancillary structure, tanks, rocket engine, all of that is just dead weight lugging around for most of the flight. Now, it's not dead weight in the sense it serves a purpose, but once that tank is almost empty, all of that structure above it that's not containing the fuel, we're lugging dead weight around. The same thing with an aircraft, by the way. We see that natural log, m naught over m1, in the Breguet range equation, which you'll become much more familiar with next year in design. So this is one of those exponential behaviors. It's exponential with ISP and then scales linearly with that. So we want to get rid of that. Now, ideally, what we would do is we'd consume our rocket as we go along. But no one's yet figured out how to build a rocket that burns itself. So what we do by staging is we literally throw away part of the rocket every once in a while. Now, each stage, that mating, that interface, adds weight, adds complexity. You need separate engines and the like. But there is a balance there. And what you find generally for stuff going into orbit is 2, maybe 3 stages is the sweet spot. Any more than that, and you're actually adding weight back into the system from all the complexity. You're also adding likelihood of things failing. The other nice thing about staging is the design of our rocket engine, specifically our nozzle, for sea level is very different than it is for vacuum. So we will see different engines or different nozzles on the same engine for liftoff and for high altitude. Now, that doesn't mean we don't create situations where you have an engine that's burned all the way from the ground to orbit, so like Space Shuttle main engine was. Used on liftoff all the way up into injection into orbit. It had a vacuum nozzle because it was much more important for it to be efficient up at high altitude. But the solid rocket boosters, they had sea level nozzles. And if you ever watch video of a launch of the Space Shuttle, you'll see all sorts of shock diamonds in the Space Shuttle main engines at liftoff because they're overexpanded. So the atmosphere is compressing that flow. And then at high altitude, right before burnout, if you look at the plume of the solid rocket boosters, they expand. They look like they're just ballooning outwards. And that's because they're underexpanded. So they're not working at their most efficient. But staging's really simple. We just build our stages up from that top stage, the payload. That becomes the payload for the stage below it, which has its stage mass, which becomes the payload for the stage below it, and the stage below that. And it's just a summation. It's very simple and straightforward. And so the delta V of stage I is our theoretical exhaust velocity of stage I. The starting mass, the mass of the stage before it, and the mass of that stage over the final mass of that stage. Now, I will often ask you what this leaves out when we're doing the rocket equation. And the two things that we're not counting here are gravity losses, so the losses of escaping a deep gravity well, Earth, solar system like, and of course drag losses. So this works really, really well when you're up in orbit, less so from the ground. But as a first approximation for the maximum delta V, it's a reasonable state. Okay. Back. The second question. This is a bit of a history of staging. What was the original reason for the 0+ staging concept? Now, the trick here is the original reason. It's not the reason we use it today, but it's the reason that the R7 had 0+ stages. It's the reason that the Atlas was a 1.5 stage rocket. So, is it to create additional payload for little additional complexity, which is 33% of you said that? Is it increase engine reliability, uncertainty over in-flight ignition, or increased commonality of parts? Now, on all of these are somewhat, well, two of these are true today, one of these was true in the past. So the one in the past is the uncertainty over in-flight ignition. We had never built rockets and engines that we tried igniting in vacuum or near vacuum. We just didn't know if it would work. And so the simple solution was you light everything on the ground. You have an engine that's designed for vacuum operation, high altitude operation as your core, and you put a bunch of strap-ons on the side that you use for liftoff. Now, today, we do 0+ for this top one and this bottom one. I can strap on some solid rocket boosters, small gems as they're called, or the like, onto the side of an Atlas or a Delta, and it's cheap, it's easy, it gives me additional payload. It's not exactly elegant, it's not the most efficient, but it's a quick increment of payload for little additional development cost. And if I'm not launching hundreds of these per year, or even 30 of these per year, it's not a big deal. The other one, and you see this with Delta IV Heavy, you see it with Falcon Heavy, is we just have duplicates. It's every bottom stage is the same, the strap-ons are the same. And then what we do to get the better performance is we run those strap-on cores, common cores, at full thrust from liftoff till they burn out. And we run the center zeros, the actual first stage. Maybe at liftoff it's run at full, and then we throttle it down for a while. After those boosters use fuel, we throttle it up again, and we get more altitude. It doesn't really affect engine reliability much at all. But yeah, the top one and the bottom one are the common ones for today, but originally with the R7, it was just because we didn't know how to ignite the boosters or the engines at altitude. And the R7's an interesting one, Soyuz. So all of these engines are actually the same. They don't have a different nozzle, but you could put a different nozzle. And I don't know how many of you look at what Soyuz looks like when it lifts off. It's in a cradle that opens up. All of that is basically held on by gravity and thrust. So literally what happens, there are little motors to improve separation. When these engines burn out, shut off, it just naturally separates. And you hold the rocket on the pad by that, so everything holds together. And then the thrust lifts it up. If you've ever seen how they ignite the engines on a Soyuz, they literally use matches. these giant electronic matches. They're wood, and they've got 2 in each nozzle, and if one fails, they can light the other one. Not particularly sophisticated, but amazingly reliable. Okay, in that first generation of rockets, why did the US use the 1.5 stage concept on the original Atlas missile and launch vehicle? Just like the R-7, which became the Sputnik launch vehicle, and then the Vostok launch vehicle, ultimately Soyuz, the Atlas was originally an intercontinental ballistic missile. It was a slightly better one than the R-7 because it only took 30 minutes to fuel instead of 3 or 4 hours. So you could react to bombers, say, coming in. But it wasn't a great one. It was quickly replaced by the Titan system, which allowed storable fuels, so you could keep it in a silo, launch it at a moment's notice. But why do we use the 1.5 stage? Because keep in mind, a 1.5 stage, instead of separating strap-ons or a whole core stage, you literally just throw the engines away. And in the case of Atlas, it had a linear line of 3 engines, common combustion chamber, but the 2.5 stage engines had sea-level nozzles, and the core engine was a vacuum nozzle. Same engine, just different nozzles. Why would we want to do that? Because that seems really stupid. We've got all that structure of fuel tanks and like. Remember, they're fed out of the same tanks. So why would you do a 1.5 stage design? In fact, it seems on paper a really stupid idea. But the key thing about this that made the 1.5 stage work, and it only works in this case, is Atlas is a fully monocoque pressure stabilized structure. It's like your energy drink can. There is no other structure that holds it together. Literally, if you remove the pressurization and you stack it vertically, it will collapse on itself because of the mass. So that's why 1.5 stages worked. And it was also a problem because literally, if anybody dropped or damaged the walls of this, it tended to explode, to collapse and explode. So you would just shed your engine and keep going up. Now, as I said before, it may have been in this session, when NASA launched John Glenn into orbit on a Mercury Atlas, so the left-hand side rocket there, the failure rate on testing of the ICBM version, about 50% of them disintegrated on launch. To the point the Air Force had basically not accepted most of the missiles into service because it wasn't deemed reliable enough to, say, kill a few million people, but it was deemed reliable enough to stick a person into space. And they never really fully solved it, but it did work over time. They're just handling. If you go to Kennedy Space Center or Marshall Space Flight Center, they have some Atlases there, and they're on their side, and you walk up to them, you'll hear constant hissing noise because they have to keep them constantly pressurized with air, otherwise they'll collapse. That's not the case for things like Delta or Atlas V or Titan. They use what are called isogrid structures, so they actually chem mill or machine extra stiffeners into the side, and it looks kind of like diamond shape. That strengthens their rockets. Okay. I think that's the end of that poll. Let's see what questions we have and see if I'm answering them correctly. There's always the chance I will answer them incorrectly. Okay. How does a kick stage of a rocket work? So a kick stage, if I remember correctly, is typically used as either an insertion stage, so it's a quick burn to just do a quick correction, either insert it into an orbit, or as a departure stage from one orbit into a transfer. Usually, they're really relatively small, but more and more common, we'll actually use, say, our second or third stage for multiples of that. One of the most common orbits that we launch some satellites into is what's called geosynchronous transfer orbit. And so that upper stage kicks it into the transfer orbit, lets go of the satellite. Then there's usually either motors on board the satellite, some of which can be discarded. Sometimes they're just kept for station keeping afterwards that bring it into and circularize the orbit. Question 2. will asteroids deorbit, slow themselves down, etc., before they hit into a planet? So I've got an lump of ice with an iron core floating through space or comet. It gets in, is sucked into the gravity well of a planet, spirals, enters the atmosphere. There is nothing in that process prior to it interacting with the atmosphere to take any energy out, right? It doesn't have a rocket motor on it. We can't slow it down that way. So the only thing that will take energy out is the atmosphere and then the surface of the planet, if there is one. Now, just like a satellite when it deorbits, same thing happens. Now, satellites are nice and not particularly dense. Even things like International Space Station, Mir aren't. So they tend to break up and burn up. But a large, heavy nickel iron core, and they are quite dense, not like spent uranium or tungsten dense, they're not going to deplete themselves completely. And that's why we get asteroid impacts. Or sometimes, because they're not actually held together all that, they're not solid, they're a conglomeration, they actually break up. And they break up, when they break up, that creates a lot of energy and force, and you get those mid-air explosions like the Tunguska explosion. And that's actually, in some respects, for a given size of asteroid, far more devastating than something that hits. Obviously, once you're the size of a shipping container or a small building, that's much more devastating. Okay? When there is a rapid unscheduled disassembly, can the second stage engine kick in and save the humans on board? I.e., when the rocket disintegrates, which, by the way, it is known to do, what happens? So see that lattice tower on the top of the Mercury? They had them on, Gemini didn't have them, and they had it on Apollo. Soyuz has a similar thing. The Crew Dragon is different in the way it's built, but it's a similar concept. That's what's called an escape rocket. And the whole purpose of that is if this rocket begins to fail catastrophically or shuts down too early, that pulls it free. And I mean, it moves you. So instead of accelerating at 3.5 G, you're talking 9G, 10G to get clear. And there is actually video, not that long ago, I don't remember how many years ago, one of the Soyuz rockets failed on launch, and that activated. If you watch the video inside the capsule, it's quite intense what they went through, but it saves them. Gemini had ejection seats. Crew Dragon uses rockets built into the side of the service module to do the same thing. And once you get above a certain altitude, where it's easy enough just to separate, they'll jettison that and the like. There is actually video of what's called the shortest or lowest apogee mission ever. It was a Mercury Redstone boilerplate mission where, due to some weird sequencing, they ignited the engines. The rocket lifted off about a foot off the cradle, and then the engine shut down, sat back down in the cradle, and instead of that firing to take the capsule away, it said, "Oh, I'm done," because the main engines have shut down, and ejected itself. And so you had a capsule and a fully fueled rocket, unstable on the pad. I'll see if I can find the video and put it up on Blackboard, and maybe we'll watch it in a couple weeks. But yeah, it was Gene Kranz's first mission as flight director. So Gene Kranz of Apollo fame, who was the flight director for the Apollo 11 moon landing. It was his first flight director mission early on. So that one, and then of course there are other situations. Obviously Space Shuttle didn't have any of that, so Challenger, it just blowed up. Like, okay. Can you go through the last question on the midterm quiz on escape velocity? I If we have time later, we will do that. Otherwise, I'll do a little one for you. It's quite simple. It's just based on the altitude and whatnot. I will check on that because it has been in the past where there's, due to a thing, we get errors sometimes. But I did go through every single one and hand calculate against some of them. So I don't believe there's an error. But if it is, it gets corrected. We correct it, it automatically corrects your marks. Okay, let's work on our second poll of the day. This one is on orbital transfer. Okay. So now we're talking about orbital transfers and some of the common orbital transfers. First question, what's the lowest energy single burn? Now, single burn's a bit of a weird one because obviously you burn into and then you have to burn out of. So isn't that, if you have only one thing, you've got two burns. But we typically consider that thing, the transfer is entering the proper transfer that gets us to the final destination. So that capture burn at the end of the transfer isn't considered part of the burns. Any of the burns along the way, they're considered part of it. It also, in this case, we're not accounting for any mid-course correction because there is uncertainty. I do a burn at the start, say, aiming for Mars. You know, any small change, burn lasts a little too long, thrust is a little too high or a little too low, I'm going to miss Mars. It's a tiny target in space. That cone of uncertainty grows and grows and grows. And we measure that in what's called arc seconds. And it doesn't take many arc seconds to miss a planet. Kind of like back in the day when we were flying from, say, North America to Europe, we used to use a navigation system called Omega. And the purpose of that was if you left Newfoundland, because that was the last bit of land, or just south of there, could you hit Ireland? Because that was where people tended to arrive just to the Great Circle routes. And that was the accuracy. It was enough over that distance that you could hit an island the size of Ireland. You think is big, but in the grand scheme of the Earth is quite small. So we have some typical ones: tangent, fast, Oman, bielliptic. Hohmann transfer, named after the German. That is our lowest energy single burn transfer. There's lots of cases, depending on where you're starting from and the eccentricities and all of that, where bielliptic transfers will actually be lower energy. So you go and you burn, you do a higher energy injection above the orbit you want to, and then come back down again with the next burn. But that requires more than one burn. Nice, simple, easy, single burn transfers, low energy. Anybody remember what the problem with these single burn low energy transfers is? Yeah. Okay, so all of these are kind of, in a sense, fictitious, and that these, like bielliptic and tangent and stuff like that, tend to require what are called impulse burns. But we can get close enough to it with some corrections. That's why we do mid-course corrections. But the real problem with the Hohmann transfer is it just takes a hell of a long time. And depending what you have on board or what you're trying to do, you may not have that time. You may want to get there much faster. Maybe you want to observe something. Or maybe you want to do, you have a payload that might expire after a period of time. You have so much liquid helium on board for your, for your telescope or the like. Now, when we're doing departures out into the far solar system, we'll do gravity assist flybys, all of that stuff. They can bring our energy down, our rocket energy down even more, but we're using the gravity, the planets around us to capture energy, to extract energy and do that. But for simple transfers from A to B, the Hohmann for a single burn is our lowest energy one. Okay. As we said, what's the major disadvantage? And the major disadvantage is, as always, time. It is also incompatible with low thrust systems. As you said, it's requires impulse type burn. Okay. An impulse burn is a burn with instantaneous acceleration, and as we said before, that's true. Now, as we said, there are no true impulse rockets. The closest thing to an impulse would be what? What would be the closest thing to an impulse burn? What would we use if we wanted the closest thing we could have to an impulse? So these are finite time and distinctly finite time. Some of these are like half-hour burns, which is quite long when you think about it, but short in the grand scheme of, say, a 6 or 9 months transfer. Guns. They are about as close to an impulse burn as we get. Fire a cannon. I mean, the duration of the burn for a cannon or a gun is tiny, tiny, tiny. So that's as close as we can get to an impulse burn. Obviously, the accelerations are obscene. Anybody know what the acceleration for a true impulse burn is? Yeah. Yeah, it is infinite. In fact, if I remember correctly, the jerk is even infinite. I don't remember if anything higher is infinite. Electric propulsion, low thrust chemical, we've got to do more sophisticated. Nice thing about low thrust chemical, if we can turn it on, the engine on and off as much as we want, we just repeatedly burn here, here, here. Just intercept that at the minimum delta V change required. Or an electric, which is even lower, the nice thing is we'll just continuously burn. If we have higher thrust, electric, high efficiency stuff, we can do kind of high energy stuff and burn all the way, flip it over, and burn the way back in. Okay? Pretty straightforward with that. Again, I'm not going to ask you to calculate an electric thrust transfer. I'm not even going to ask you to do any maths on transfers per se, but we may talk about and ask you about these transfer orbits and some of these assumptions and the like. Okay, anything more in Q&A? How does Lunar Gateway work? Why is there a need for HLS, and how is it different from ISS? Lunar Gateway. Lunar Gateway is an interesting one. The concept comes up for many different reasons. One of the reasons we do Lunar Gateway type things is that theoretically we can get more payload onto the lunar surface if we kind of collect stuff together. So you lift something off without all of the fuel you need to do landing and departure from the moon. So we can do that. One of the other reasons we talk about Lunar Gateway is there's actually the idea that the fuel that we're going to use to get on and off the moon isn't fuel brought up from Earth. We would collect it from somewhere else. And then the final idea, and probably the least useful, is use Lunar Gateway as a staging point for Mars. Now, outside of collecting fuel from the moon, so hydrogen from the ice on the dark side of the moon, outside of collecting fuel from the moon and bringing it to a gateway that we then use to refuel a rocket that's been boosted from Earth, it really doesn't make sense because all of the delta V's you've got to do to get to the moon. So we'll talk about that in a second. Okay? One of my favorites. So there's all sorts of stuff. And the idea is it just allows us to get more payload on and off. It's different from the ISS because it's a completely different orbit. The ISS is a shitty orbit for anything, including the ISS. The ISS orbit is a compromise between the launch capabilities of Space Shuttle and Soyuz. The inclination's too high, so Space Shuttle, to get meaningful payloads, it had to lower orbit. Soyuz couldn't go any lower inclination at the time, and the like. The original American plan was obviously 28.5 degrees for inclination. Space Shuttle would have been several hundred kilometers higher for that. Okay? Okay. What orbit is Tesla in? I don't know exactly. It's obviously Earth escape, but I don't think it's solar system escape. There are only, is it 6 objects that have been put on solar system escape trajectories? So the 2 Voyager spacecraft plus their final stages, upper stages, and then the New Horizons spacecraft in its upper stage. The New Horizons is a Pluto mission, but it's just easier to just send it out as part of the process. Is there a need for artificial gravity in long-term space flight? Does spinning the rocket for artificial gravity affect orbit changing? So that's interesting. I would argue that if we really are going to explore the solar system in any way, shape, or form, anything beyond Mars or anything like that, we do need to generate artificial pseudo-gravity on a spacecraft. Now, if we spin a spacecraft, in fact, just like a gyroscope, when you have a gyroscope, you have to push in different ways. But that's relatively well known. The real problem with spinning a spacecraft up is if your radius is too small, you get horrible, horrible tidal effects. So what happens is, if your feet are on the floor, which is the outside, and your head's sticking to the inside, the acceleration of your feet is very different from your head. And it's not exactly nice. If you lie in the curvature of it, it's not so bad. There's a ride at Epcot Center in Disney World. It's gone under various guises, was Mission to Mars at one point. And one of the things they told you not to do during the ride, and they had the intense and less intense, but mainly on the intense version, is they told you not to lean forward. The main reason is it's a centrifuge. It spins that creates the gravity like from launch, the force of launch and all of that. And if you lean forward, it's such a short arm, the acceleration, just by leaning forward a few inches, the acceleration in your head is very different from the rest of your body. And it has a really nasty tendency to make people ill. Coupled with, if the graphics are at all out of sync with the motion, you don't realize it on the ride, get off, and all of your lunch comes up, and Disney is not particularly a fan of large piles of vomit in the middle of their theme parks. But yeah, from a bone density point of view, it makes a lot of sense. In fact, the original plans for the ISS, there was going to be an artificial gravity laboratory module, and there was talk about at least some of the experiments having some of the astronauts sleep in there or exercise or do stuff in there versus in other places. Okay. Last survey, or last primary survey, miscellaneous stuff, and then we'll quickly go on to the last one. So we're about propulsion. So there'll be no audio for a bit. Next week's all about propulsion, and then the week after is artifacts of import. When you watch that video, one of the things is out of date. So the first question, which bit's out of date from the past? And it's only this past year that it went out of date.